Let's see, the title of the talk is Taking the Red Pill and Going Down the Rabbit Hole of Deep Learning. That's a mouthful, I get it. In case you didn't get the reference, it's from the movie The Matrix, where Morpheus gives Neo the red pill and you know it. So just like the Matrix, in deep learning there are rules that you can bend, rules that can be broken, and things like that. The problem is we just don't know any of the rules at all, for the most part. So it serves as a nice analogy. So let's get to the real thing. Firstly, why you might think deep learning is difficult. It's too mathematical. That's the one singular thing people say. Deep learning is very mathematical. It has a steep learning curve. And there are so many smart people in the domain, how would I ever make a difference, right? Well, here's the thing. When people say that you need to understand machine learning and everything before you learn deep learning, that's absolutely a baseless statement. People can't explain you deep learning because no one knows what is deep learning. That's the essence of the matter. No one knows what's going on in the field. Like there's this very, I think his name is Richard Feynman, yes. Richard Feynman said this about quantum mechanics. If you think you understand quantum mechanics, you don't understand quantum mechanics. In case, just like that, if you think you understand deep learning, you don't understand deep learning. I'm talking about deep learning architectures that spans huge layers, like 40, 50, 60, 100, stuff like that. So rather than, let me just give you an anecdotal counterexample. Everyone know who she is? Yeah, like many people know her as the actress from Twilight. I know her as a person who can only make a single facial expression in her entire lifetime. But what you might not know about her is that she published a paper in deep learning. Yeah, that's yeah. It really hurts the ego, to be honest. But the point I'm trying to make is if someone whose prospects for procreation lie in the narrow range of vampires and werewolves, and even they can understand deep learning, I am pretty sure, I'm most confident that all of you here can. So let's get into the actual talk. The story so far. It all started in this 1943 when Germany was hell-bent on destroying the entire world. This also happens to be the same the year where the German operation got totally thwarted. Anyway, so the electronic brain was developed by the McCloud and Pitts. I can't pronounce their name very well, so do forgive me. This one over here is a neuroscientist. This one over here is a computer scientist. You can see that we have no social lives. You can just see the facial expression. Just see, that is the face of a man who has lost everything. See, this is basically the architecture they came up with. Very simple architecture. You have inputs, you sum them all up using some weights, you get the output, and then you do something similar along the lines using this equation. Just sum them all up, add a bias, add a nonlinearity, and you get the output. But there's one problem. When they developed this model, there was no way of training this. And finally, people actually used it in something called the perceptron, or the Rosenblatt perceptron. Frank Rosenblatt was the first person who came up with algorithm, or rather implemented an algorithm that actually makes this model viable for usability. So how it works is you have inputs, let's say x1 to xn. You add them all up and vary them, like you add them all up by weighting them with different weights. That's why probably we call them weights, I suppose. And like you weight them up and then you add all of them. You add a non-linear function at the end and you get the output. Now till this point it's pretty straightforward. It is the same electronic brain, the McCall's and Pitts model that you have been using. The difference over here, however, is that you also have an error function. And this error function tells you how to update the weights. And how you update the weight is by this equation. This is basically the Wi plus 1 is the new version of the updated version of Wi. And this is the derivative of the error function with respect to the weight. And eta is the small learning rate. Now do realize that this algorithm called stochastic, it's not stochastic, it's just gradient descent, but it is used here in a stochastic manner, so it's stochastic gradient descent. So this algorithm forms the backbone of the entire thing that we do, like quite literally. This is one of the most simplest algorithms you will ever encounter. This is used in optimization in mathematics. This is used in several machine learning algorithms, starting from logistic regression, some of you might know it, and also in deep learning when you're updating the weights. So, and it worked, and it really worked for some of the domains. In fact, it was so good that Frank Rosenblatt said this: the perceptron is the embryo of the electronic computer that the Navy, so he was working for the US Navy, expect will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Unfortunately, as good as Bryan Adams' song "The Summer of '69" was for us computer scientists, this was the winter of '69. So, there has to be some sense of humor, right? So basically, this is a very nice analogy for the perceptron. It's like the Eddard Stark. So in case you haven't watched Game of Thrones, sorry for the spoilers. So then, in 1969, Marvin and Minsky came up with this book called Perceptron, where they basically said that this problem, also known as the Zohr problem, cannot be done in any manner by the perceptron training algorithm. Now, any idea why? Exactly, let's see a chocolate. I always wanted to give one chocolate first. My aim is very bad, so please forgive me. So, yeah, this cannot be done by the perceptron. And they gave a theoretical proof, and this basically destroyed all the love and enthusiasm we had for perceptrons. And for nearly 2 decades, no research was done in this field. So this was the very first AI winter that we ever experienced. But human beings are curious creatures. We find ways to get on with our lives. So in 1986, the ice begins to melt, and you have the Godfather. That's Vito Corleone, man. As much as I like his character in The Godfather, when we are referring to the Godfather of deep learning, we are talking about Geoffrey Hinton. I mean, this man is not just one of the foundational fathers of deep learning. He's basically the foundation of deep learning. Like, let me just give you an example. If you're a student of mathematics, and if someone comes up to you and say that, okay, this is a mathematical theorem, who do you think invented or discovered it? Discovery is a correct word. Discovered it. So, and you say Euclid, you would probably be right, most of the times. In deep learning, you would be right almost all of the times. That is just how important this man is. And he's still alive, by the way. So he's not dead. So Geoffrey Hinton came up with the idea of neural networks that we still use today. So what exactly are neural networks? So he published this paper called Learning Representations by Backpropagating Errors, which later became known as the backpropagation algorithm. So this is the general structure of the neural network. You have inputs, like over here x1 to x6, and let's say you want to classify between a dog and a cat. And what each neuron is going to do is act just like a perceptron. You're going to add them up. AI is the input. You're going to add them up with some weights and add some nonlinearity to it. And you're going to take the output. So you're going to go from layer 1 to layer 2 to layer 3 and finally make a prediction. But this is not the grand achievement of the paper. What the paper really achieves is how do you train this neural network? I mean, you can train this part. This is pretty simple. You can just use the perceptron training mechanism to work on this area. But how do you train this part? How do you train the hidden layers? It's not so obvious as how you would do it. And how you do it, now this requires a certain level of mathematics. So please pay close attention to this. How you do this is by something called backpropagation. I told you that I would not torture you too much. But in all seriousness, the topic of backpropagation would require a lengthy amount of time. So what I am going to do is I'm going to give you all a link. I think Shubham will give you a link after this talk. that is going to redirect, that is going to take you to my blog where I've explained in full detail how this algorithm works if you want the full fleshed out mathematics of what exactly goes on as a neural network is training. But what if an interviewer asks you, this is the question, this is the answer you should tell him, because chances are even he doesn't understand, and no one understands it. So, but this is not good enough. So what happens? So if you have a neural network like this and you want to train it on something, so if you start the training, you would observe something like this. The layers that are very close to the output, they get trained quite fast. And while the other layers, they're training, but it's training slowly. Are you guys being able to realize this is actually training? So that's how bad the neural networks were when it was first discovered. It trains bloody slowly. So what's going on? You were expecting to train a neural network. What you got was an animation of trickle-down economics rotated by 90 degrees. And so very few people got the joke. That's disappointing. Okay. So finally you get this trained. So the neural networks could not be scaled because of something called the vanishing gradient problem. So what this is? Okay, first let me just clarify what the gradient is. You remember in the first equation you saw the derivative of the error function. Now just assume you take all the derivatives and just stack it into a vector. That's basically a gradient vector in the most non-technical manner. So why this happens is because of this. So you have an activation function. The activation function people used at that time, and a very well-known activation function, is a sigmoid activation function. And if you find the derivative of this function with respect to x, it is just this function multiplied by 1 minus this function. And realize this function can take a maximum value of 1 and minimum value of 0. So the maximum value that this can ever take is 0.25. So every time you perform the backpropagation algorithm, this value will get multiplied to the next layers and to the derivative of the next layers. And what will happen is that as you go up the neural network, you will see that the gradients of the very first layers are so small that it's almost impossible to train them. And that is the reason at this time that it was very difficult to train these neural networks. But again, in 2006, the restricted Boltzmann machine came into the picture. So what exactly does this do? Suppose you have inputs like this, or let's just say neurons like this. What you do is you train the next layer using something called a contrastive divergence, something whose mathematics is going to be beyond the scope of this talk. But the good thing about this is one restricted Boltzmann machine, and there really shouldn't be any arrows because this works both ways. This is an unidirectional model. So this works both ways, and once you are done with this, you can just keep on stacking new layers like this. And you can create incredibly deep networks called deep belief networks. And what is even more impressive about this is an unsupervised learning. So it's as if the network is hallucinating, because over here you're not using any supervised training over here. You're just using this, you're just stacking these layers up and just like pushing this contrastive divergence algorithm and training them 1, 2, 3. And after this, what you can do is you can add a neural network, and you would expect the output of this deep belief network is slightly better than what you would expect from your actual input. And that way, the neural networks gives you a slightly better performance, to say. But the problem with this is, again, it doesn't solve the vanishing gradient problem. And this approach is not that great either. In fact, in 2010, there was a new paper, support vector machines, that came out, and the support vector machines easily beat this. So, and after that, in 2012 is when you finally have the real emergence of deep learning. The restricted Boltzmann machine first embedded the term deep learning, and then after in 2012, you have the AlexNet, and that is where modern deep learning techniques emerge. This is the entire architecture. You have 1, 2, 3, 4, 5 convolution layers followed by 3 linear layers. And another thing is that this work is divided between 2 GPUs. So why AlexNet makes neural network great again? Well, firstly, the use of convolution layers. This is a convolution operator. If you want to see a more graphical version of this is how it works. It is like a time-weighted version of this FT by this function g minus not t minus g minus tau at the moment t. But in most practical applications, we don't exactly use this formula. What you would expect in deep learning is something like this. You have an image, let's say this is a binary image, and you have a kernel that kind of slides above the entire image, and you get a convolved feature as the output. So this is basically what the convolution layer does. It takes an image, it kind of slides a kernel, and you get the convolved feature. And it really works well if you're working with images. In fact, it works so well that in most deep learning architecture, if you just stack new convolution layers one upon the other, you can pretty much do anything. And that's the reason I think deep learning is so difficult to understand. It's so convoluted with these convolution layers. And that was a very bad joke, I think. And another thing is that these people used another activation function called the Rayleigh. And this does solve the vanishing gradient problem. Now see, this is the sigmoid function. And as I told you, the derivative of this function leads you to that vanishing gradient problem. But if this is a Rayleigh function. And one thing you would notice is at this point, this function is not differentiable. So what you do is that you find the derivative of the Rayleigh function using something called a subgradient, which I'm not going to go into. But if you just want to understand what it works is that if z is less than 0, just give it the derivative is going to be 0. If z is greater than 0, its derivative is going to be 1. And when it comes real close to this point, you have 2 options. You can either go for 0 or 1. Generally, you just push it aside by some sigma, by some epsilon. You generally never encounter the scenario where the z value is exactly 0. But this really solves the vanishing gradient problem. But it introduced another problem into it. It's called the dying neurons or something. I forgot the name of it. Generally, what that means is that if z is always lesser than 0, this is always going to fire a 0 value. So it's going to be like a dead neuron through the entire training process. So in order to solve this, you use another function called the leaky Rayleigh, which is just a slightly bent version of this. So this is a horizontal line. You just bend the line a little bit, and you have it. Leaky Rayleigh function. Another very interesting thing about dropout regularization is the use of the dropout regularization. So this is a neural network. What dropout regularization does is, with probability p, you don't train the neuron at all. You just leave them aside. Like it's like a lazy person was programming this, and they thought like, why do I bother training with all of them? Just leave some of them aside. Just don't train some of the neurons, and this gives really nice accuracies on validation. And so the problem with neural networks is that once you create this deep architectures, sometimes it's possible that the neural network is going to memorize the entire training data set. And in order to stop that, you use something called a regularization. And what dropout regularization does is that, okay, just don't train some weight sometimes with probability p. And it decreases the training period. It increases the training period, but it also gives very nice accuracies when you are testing the network. So the thing about this is stupid ideas do work in deep learning. So this was a very stupid idea if you just look at it, but it works. And finally, the use of GPUs for computation. So why GPU? So you have inputs x1 to x6, and the outputs are just this summation of all of them, like that. And if you want to represent it as a matrix, you can do it like this. So yeah, even neural networks are nothing but linear transformations, isn't it? So you cannot escape linear algebra in computer science. It comes up everywhere in quantum computing, in neural networks, everywhere almost. So you can replace an entire operation of a neural network just by matrices alone. And you can assume that these things are just a vector input. Not only that, one good thing about this is that once you're computing this with this, you can simultaneously and parallelly compute this with this. So GPUs are exceptionally good for tackling this problem. And not only that, you can like take batches of inputs. Why stick with one input? Take batches of inputs, do them parallelly. You have thousands of cores in a GPU. And so this is the reason why GPUs are so important. So can you tell me which other application extensively uses GPUs? Exactly, who said that first? Oh. Okay. So, and that is also the reason we wanted you to attend the gaming sessions, because gaming is important. See, even if you don't want to go to deep learning and still want to help us, like become a gamer. You're going to help us, man. The video gaming industry really propels a lot of the things in deep learning, thanks to the hardware achievements and everything. That's true, but you know, this is India, and this, so the government just said some. Even I want to do that, by the way. So some of the most successful ideas in deep learning are the recurrent neural networks. So you have a neural network like this. You have some outputs, and what the recurrent neural network does is just take the outputs and feed it back in. And this architecture is called the recurrent neural networks. But what is even more interesting is that if you go through the literature of this, the back propagation of this is called the back propagation through time. And that sounds absolutely cool. Like just go through the literature. It's back propagation through time. It's as if that you're going back in time or something. But just then you realize, no, it's just matrix multiplication and stuff. Our very successful variant of this architecture is the LSTM. I'm sure some of you have used them. It's excessively used in NLPs and even in images. Sometimes it's being used. Another very interesting approach is the autoencoders. So you have an image of a dog, and you want to squash that image into as small of a region as possible and get back the reconstructed version of that image. So this is not a lossless compression, by the way. This is a lossy compression. I heard you guys. I mean, come on, lossless is useless. Like, if you want to use a lossless compression, why are you doing deep learning? Like, you have so many better algorithms for that. I mean, you want a lossy compression because you see, these things are rather useful. Because if you can reconstruct this image, not to the same accuracy, I mean, if you can reconstruct this image, it means that you're capturing some essential features of this image. And you can then later use them for pretty nice things like image classification, like segmentation, whatever. Another really nice thing is the modification of the autoencoders into variational autoencoders. What it does is that you take this part and like you send it to two different networks. That one is going to calculate the mean vector and the standard deviation vector. And you join them together and you have a sample latent vector. So rather than taking the entire image, what you will get is a probability distribution. And once you train this entire neural network, what you can do is you take this out. This is the sample latent vector. You just change them a little bit, and you can create very nice images. Like you can generate a lot of images using this technique. And this has been one of the best ways of generating images and for a very pretty long time. But when you're talking about generation of images, the one thing that rules them all are the GANs, generative adversarial networks. Very interesting thing. So what it does, it plays a game. Yes? Alpha, beta, beta. No, this is not an alpha beta kind of game. This is just going to, you just have a value over here, and this player is going to try to decrease the value, and this player is just going to try to maximize the value. It does not involve that complicated things. What is complicated, however, is this function. So before getting into what this function does is, let's just let's just give an architecture description of what it does. So you have random data, you feed it to a generator network, you get some output data, you have real data, and you feed this to a discriminator network along with the output data that you get. And the discriminator network is supposed to predict whether, okay, this should be data, but never mind. Okay, the discriminator network is supposed to predict whether the data that is given to him is by the generator or whether it's a real data. And then you train this neural network. So this is where this, and now let's talk about this equation. Okay. So firstly, when you see something like this, it's an expectation. If you're thinking about implementing them, just think about averages. That's the simplest thing you can do. This is an average function. So what this means is that you sample data points x from the real data, you take the log of them, and D is the discriminator network. So D of x is going to give you some value between 0 and 1. That is kind of like whether signifying whether it's believes that this is a real value or whether this is a fake value. And you take the average of this. Similarly, you take the output of the generator, you feed it to the discriminator, you get whatever value you can get, and you subtract it from 1 and take the log of it. So basically, this is what it's saying is that you want to also find out how good or bad the discriminator is thinking about the fake data. So when the discriminator tries to maximize the data, it is going to try to maximize this value and minimize this value. And the generator is going to try to maximize this value. So generator is going to try to fool the discriminator network as much as possible. And the discriminator network is going to try to learn to better itself. And in the process, you can get magnificent images. I'm going to show you one of them just now. But first, let's just give you a practical demonstration of how it happens. So the data that you're given over here is a Gaussian distribution, a one-dimensional Gaussian distribution. This orange line is the decision boundary, and this is the normalized histogram of the output of the generator. Let's just wait for this. Yeah. So as you can see in the starting, the discriminator was pretty powerful, but then soon the generator network was able to identify, grasp the actual Gaussian distribution, and then the discriminator network can no longer make sense whether the data is coming from the real value or whether the generator is producing it. And using this idea, you can create fascinating things. These are the results that you would obtain if you train a cycle GAN. Now, I'm not going to go into the detail of a cycle GAN, but it is a variant of a GAN, and this is and these are the images that we got in the project that we did in our last semester. So you take in an input of an image, it is going to output its equivalent photorealistic image. Just look at this. Like, it's almost hard to tell whether this is actual photo or this was generated by the GAN network. Similarly, if you give it a photorealistic image, it's going to output a portrait of sorts. This has been trained by Monet's painting, if I recall correctly. 1,000 of Monet's paintings and 6,000 of real images. Now, this all is fine. Now, I understand what you guys are thinking. This was an absolute waste of time. I didn't really learn anything much. So here's the thing about deep learning. Remember what Morpheus said to Neo in the Matrix. No one can teach you what the Matrix really is. You have to experience it for yourself. In the same manner, no one can teach you deep learning exactly. You have to experience it for yourself. So there are easy ways of doing it. You can either go the easy way. Some of you might have done it. You might have gone for TensorFlow, PyTorch, and all these frameworks. The hard way is you acquire the fundamental knowledge. That is the machine learning and probability and matrices and all those things. But the payback is really tremendous. And my advice is just start by implementing the backpropagation algorithm and implement a neural network from scratch. This will really help you in the long run. So what I will give you is an assignment if you choose to do it. First, understand the backpropagation algorithm. That will give you a link to it. Then you'll have to learn a little bit about the cross-entropy loss function that Anirban touched yesterday, slightly. You'll find it, don't worry. Now create a neural network that is going to learn the logic behind the fizz buzz. Anyone know what is a fizz buzz? Okay. So the fizz buzz logic is like that. You have an input. If it is divisible by 3, it's going to output fizz. If it's by 5, it's buzz. If it's 3 and 5, it's fizz buzz, or else it's just output the number. So let's have this modification. Let's have this specification of the neural network. You have one input layer, one hidden layer, and one output layer. The input layer will have 10 neurons. It's basically the binary representation of the number that you want to feed it to. You have 100 hidden neurons. The output will have 4 neurons. And just for simplicity, use sigmoid in all the layers. I mean, it's just one hidden layer. I don't think that the vanishing gradient is going to affect that much. And then use the cross entropy loss function on this. And what the cross entropy loss function is, well, I can't go into it, but what the cross entropy loss function basically talks about is basically if you have, for a binary setting, it is derived from the Bernoulli distribution. So long back, we realized it's much better to deal with probability, to minimize, to deal with probabilistic loss function rather than minimizing accuracy. So this cross entropy loss function comes, binary cross entropy loss function comes from the Bernoulli distribution. And it's very easy to extend it to 4 cases right over here. And like test it for using the numbers 101 to 1000, just train the neural network. Have some fixed training rates and just train the neural networks. And test it for 1 to 100 and see what you can get. And report the accuracies if you choose to. I mean, it's not a compulsory, but you can. And what one-hot encoding is something like this. So the first neuron is going to represent the phase, the second one buzz, the third one fizz buzz, and the last one as else. So this is kind of like a short assignment that I can give to all of you. And yeah, see what you can do with this. Thanks for listening. Any questions? Did I overshoot the time or did I undershoot it?